Thanks everybody for attending this webinar. I'm really excited to be here to present to you about this new addition to our software offering. Before starting telling you about the unbiased verification things, I would like to mention a few things about ACDLabs for the people who probably have not heard a lot about the company. So the company was founded in 1994, and currently there are more than 150 employees worldwide. The headquarters of the company are in Toronto, in Canada. You can see the nice picture of the CNET Tower there. We have sales offices in Canada, in the UK, in Germany, in France, and in China, and we also have a global network of authorized distributors. We are developing all our software in-house. We don't rely on modules that we purchase from other third parties. And this way we have full control of the quality of our software, and we don't have to make compromises in our software to accommodate for the external modules. The company is privately owned, and when it started in 1994, the first products that came out were the now very famous NMR predictors, the ACD name program to name organic compounds according to IUPAC rules, and also the pKa predictors. The company has moved quite a bit since then, and there are many more offerings right now. The current offerings can actually be divided in two main parts: the ACD Spectra platform for all types of Spectra data processing, analysis and the data management, and also we have the Percepta platform for general phys chem and admitox predictions, so way more than the early offerings that we had. We offer full support for all the major analytical techniques, including chromatography and LCMS. We have ongoing collaborations with all the major instrument manufacturers, and you can see here a list of instrument manufacturers. I'm sure you will find that you have instruments from these people in your labs. And we do this in order to ensure that we correctly import the data generated by their instruments, and we keep our format support current. It's not that we worked once with them and got a piece of information. We keep on working with all of them. We can, and we have through the years, through our professional services department, integrated our software with all sorts of analytical instruments so that we can retrieve the data once it's generated and manage it. We have moved on from the simple interpreting of individual pieces of data to providing the facilities for total information and knowledge management in an efficient way. This leads us to have better support for making, and you to have better support for making the right decisions in a time-efficient manner. All of these are done through the use of the multitude of options in the ACDLabs ecosystem. And it was part of this general knowledge management that we've been moving on that we started with structure verification. Structure verification started for ACDLabs much early. It started probably in the mid to late 90s. And back then we had the platform that was called ACD NMR Manager. And that was when we first introduced NMR structure verification. Initially it was done only with proton spectra, but as time passed we introduced multiple spectra and 2D spectra. In 2011 ACD NMR Manager evolved into ACD Spectrus, and that's when we introduced the Spectrus platform. And in 2014 we released the first big evolution step in NMR structure verification, what we call combined and concurrent verification. Now, in 2017, we are introducing the unbiased verification module, which I will be talking to you about. So, let's imagine for a minute that we have a synthetic route, and we are aiming to go through several synthesis steps to synthesize the final product. And in the end, what we want to do is we want to ensure that we have the correct structure here. And what we do for this is we record a series of spectra. We record MS spectra, we record NMR spectra, and then the question that we have to answer is, are all these spectra, the NMR and the MS, that is, in agreement with the proposed structure? In order to do this, we can use the standard structure verification tool, and we enter the spectra, we enter the structure, we click the button, and it tells us a match factor. In this case, it says 0.85, which indicates that there is an 85% chance that this structure match is the proper one for this spectra. Now, just a word of caution, the 85% is calculated based on the worst matching signals. So if you have, let's say, 20 signals in your molecule, in your structure, and you observe correctly 19 of them, but one of them is wrong, then you will get a very low score because you are missing a signal. So having a score of 85%, 0.85 match factor, is a very good score, and for most people this would be sufficient to show that the structure is the correct one. However, there is still some doubt. So sometimes, there may be something, a slight modification that would not be very evident in the spectrum. So the next question is, will other similar structures agree with this spectra? And we answer this by using the tool we refer to as combined concurrent verification. And what we do here is we can ask the software to automatically generate isomers and test them, or we can also input ourselves isomers. And we see here in this example that our original structure got a match factor of 0.85. There is another isomer that got 0.73. So 0.73 is still a high score, so it could have been considered to be good. However, we have the 0.85, but other structures we see get very low scores and quite a few error messages here. So this increases our confidence that we have the correct structure. However, there may still be doubt. We may still have done something wrong. And in the end, we have to answer the question, what is the structure? If we look again at this scheme, all these previous methods we described assumed that this is indeed the general skeleton of the molecule. And we are basing all of our analysis on the fact that we are looking for this particular structure. Now, what if somewhere before here, some of these steps didn't quite go as planned? So, for example, this reduction here maybe reduced something here, or this dehydrogenation maybe affected this nitrogen here. How can we be sure? It can be that there is a very lucky coincidence and the final product is maybe different to this, but still has the same molecular weight. So in order to deal with such cases, we are introducing our tool, the unbiased verification. And what we are doing with unbiased verification is we are taking the spectra that we use to confirm the structures, and we are feeding them into a computer-assisted structure elucidation system. So we don't, we are using our computer-assisted structure elucidation, which we were the first ones who introduced usable case systems, and we are feeding the spectra into this system. We are also feeding the molecular formula of the proposed structure. Be careful, we don't feed the proposed structure, we just use the molecular formula, and the molecular formula is something that we are usually very confident about because we have recorded it most probably with a high resolution mass spectrum. We feed the molecular formula. The software then gives us the option to select a fragment because there is a very good chance that we are confident with one particular part of the molecule, but we are uncertain about the rest. This is an option. We may or we may not select a fragment. Then the system will estimate the difficulty and tell us whether we want to proceed or not. So this sounds quite nice. And yeah, what are the requirements for this to work? First, you need to have ACD NMR Workbook Suite version 2017 or later. You do not need a special key for this, so you don't have to buy an add-on to have this. It is included with NMR Workbook Suite. If you have one of the earlier versions and you are on maintenance contracts, then you are entitled to get it, and you can get it and try it. The second requirement is that the molecular formula should have a molecular weight of 400 or less, and it should not have more than 20 carbon atoms or 22 carbon and nitrogen atoms. We are doing this in order to ensure that the solution will come out in a reasonable amount of time. The third requirement is that you must have at least a 1D proton spectrum, a 1D carbon spectrum, a 2D HSQC spectrum, and 2D HMBC spectra. Okay? And the final requirement is that you must have a fully assigned carbon-13 spectrum, which should most probably be the case if you have reached the point where you have already verified your proposed structure. So I could keep on talking about this. However, I think it's better if we go and show you the software in action. So let me end the slideshow. And we see here an example data set and a proposed structure. And we have quite a bit of spectra here. We have the proton spectrum, we have a COSY spectrum, we have an HSQC, we have an HMBC, and we have a carbon spectrum. And let's answer the first question, whether this structure fits this spectra. So I'm going to click the automatic assignment button, and we see after a little bit that we get a match factor of 0.76, which is a very good match factor. And it may seem a bit low, but if you consider the amount of information that we have here, it's actually pretty high. And I'm saying this because we have here experiments like the HMBC, where you may be expecting to see one peak and you don't see it for whatever reason. Or you may not be expecting to see another peak, maybe a very long-range correlation, and again, for whatever reason, you see it. So this uncertainty on how the information comes in is what contributes to having a relatively, at first glance, low match factor, but it's actually a good one. And in fact, if you look through all the spectra, they are very good spectra, pretty high signal to noise, very nicely resolved peaks. And I could dare you to try to find some evidence that this structure is not the correct one for this. You will not find, I'm very confident in this. Now, let's say though that we have some doubts. What could we do? Let's activate the combined concurrent verification. And I'm going to say here, test concurrent structures, and I'm asking the system to generate 5 isomers. I'm going to click the Run Auto Assignment. Oops. And after a very little bit, the isomers are generated. And we see here that our proposed structure got a 0.76. Everything else is lower. There is one with a 0.49. The rest is actually at 0. And lots of error messages all over. So this further increases our confidence that this is the correct structure. But is it really? Let's see what unbiased verification has to say. Unbiased verification is activated just by clicking this button here. So I'm going to click this button. And at first it tells me that there are several structures attached to the project, all these ones that were generated, and it will only use the current structure. So the first one, that's fine. I click OK. And the next question that the system asks me is here to select a fragment. I can select a fragment, or I can leave it without selecting a fragment. If I leave it without selecting a fragment, it's going to be, let's say, very truly, purely unbiased, but it will take longer. for the purpose of this webinar, I'm going to select this fragment here. So just with the lasso tool. And this is a very safe fragment to select. I'm very confident with it because I have signals for all these 4 carbons from the HSQC spectrum, and I have very good correlations in COSY. So I'm fine with this. I don't believe that there is any way that this fragment is not correct. So let's click OK, and immediately the system tells us that the problem is estimated to be easy and asks whether we should start generation. I'll start generation, and the spectra and the proposed and the molecular formula are fed into the case system, and after a very little bit of time I get the result. The structures are generated, they are sorted, and I get this quite surprising message that the proposed structure has been generated and has actually been ranked number 4. So there where we were before, we were very confident about the structure. Suddenly we see that there are 3 other structures that are better. Let's see what's happening. We see here our proposed structure, and we see the 3 structures that are ranked higher. The number to look at now is this one. There is no match factor here. You look at the mean deviation of predicted versus experimental carbon and proton chemical shifts. And we see that for the proposed structure, this deviation is at 5.6 ppm, which is a relatively high number, while the best structure has a deviation of 3.7 ppm. And the others are higher than the best structure, but still lower than our proposed structure. If we look at the difference between the 2 structures, the difference is that this peroxide bond is actually sitting on the bridge here. It's not on the side. So this is the type of difference that could make this structure invalid, even though the spectra are correct. So we see here how unbiased verification produced the correct result, and how it gave us a structure, an alternative structure, which is actually better than the one that we were proposing. So going back to our presentation, we see that our structure has been generated and ranked number 4, and this is the essence of unbiased verification. So in concluding here, we should say that the unbiased verification is an extension of the structure verification tools in ACD NMR workbook suite. It comes naturally after the automated structure verification and combined and concurrent verification. Unbiased verification offers the ultimate tool in structure verification. It is the last thing you can do if you want to be completely sure about the structure based on the NMR spectra you recorded. Now, for those of you verifying structures and doing structure elucidations all day, you know very well that it's very easy to prove that a structure is wrong, but it's in fact very difficult to prove that it is correct. In fact, you are proving that a structure is correct by not being able to find any other evidence that the structure is wrong. So the more clues that you have that the structure is the correct one, the better. In any case, you don't necessarily want to proceed with the wrong structure, and you may have heard about the case of bosutinib. If not, then you can have a look at this reference from Chemical and Engineering News and all the problems that existed with proceeding with a structure that was assumed right but was actually wrong. So finally, I'd like to thank you for attending this webinar, and I would like to ask you to sign up for the ACDLabs news and updates, and stay posted for registering for our next webinar. So I think, Brent, we can continue with any questions that we have.
Yes, thank you very much, Dimitris, for that presentation and demonstration of the unbiased verification tool. We have a few questions that have been trickling in. So we'll start with the first one here. Is it obligatory to always follow the workflow that you've shown, or the order of steps that you showed here in the webinar? So doing the single structure verification first, then the CCV, and then UBV? Can you comment on that?
Yes, it's not fully obligatory to follow all this workflow. So you can, for example, skip the CCV if, for example, there are no reasonable isomers that can be generated. However, you will need to have, as we said in the requirements, a fully assigned carbon-13 spectrum. And this is what probably an automated structure verification step will help you with. But you can definitely do your manual assignments and then proceed with the unbiased verification.
Thank you. Question 2 is, does this tool work with other nuclei such as N15 or fluorine-19 spectra?
Yes, the tool will take all possible spectra that can be used. So it will take definitely nitrogen-15, it will take fluorine spectra. We have some advanced routines in there for dealing with the fine fluorine couplings that may be present. And yeah, we are trying with all sorts of cases and examples all the time.
Okay, another question is, will the molecular weight limit and carbon count limit eventually be raised with this tool?
That's a very good question. And initially the thoughts were, that we should probably not have a limit, but in the end we found out that we need to have a limit to ensure that the structures that are generated in a reasonable amount of time. We did some internal surveys based on our customers and the type of molecules that they are using, they are studying, and we found that approximately maybe close to 80% fell into these categories. So molecular weight below 400 and carbons and nitrogens not more than 22. Now, if we see, an increased demand, we may consider to raise the limits. However, probably the determining factor will not be that much the size of the molecule. It will most probably have to do with the quality of the spectra recorded. So do you see enough peaks on your HMBC spectra, or you have a structure with only 15 carbons, but it's ranked as difficult and it takes quite a bit of time to solve. So that's something that we will definitely re-examine in the future, but for the moment it stays like that.
Perfect. I think this next question is somewhat related to the limit 1. It's basically wanting to know, what is the main difference to our structure elucidator tool or our full-blown case system?
Yes. So that's a good question, actually. Our full-blown case system, the ACD structure elucidator, is, I think, probably the first introduced case system. And as you said, Brent, it's fully blown case. So it doesn't have any of these limitations. You can have as many carbons and nitrogen as you wish. And if you look into our elucidation of the day page, you will see some quite remarkable structures that have been solved. The structure elucidator doesn't have the requirement to have all the spectra. You can have fewer spectra. So some simple structures could be solved even with only an HSQC spectrum. Of course, it will take longer, but structure elucidator will solve it. And you don't need to have a 1D carbon spectrum, for example. So it's a very much more powerful tool. And also the structure elucidator doesn't have the limitation of defining only one fragment. You can define several fragments, and in this way you accelerate the solution even more. Also, the structure elucidator offers the advanced tools for dereplication. So we can search into PubChem and ChemSpider libraries to find reported compounds with similar carbon spectra, and this way find out whether the structure we are looking for has already been reported, and if not, maybe find some fragments and get ideas on how it will be like. So even though UBV looks very much like structure elucidator, in fact it is using the engine of structure elucidator, there are still some very, very good reasons to use the full-blown case system from us.
Thank you, Dimitris. In your answer there, you answered a couple of other questions that came in, so I'll just mention them here. The question was, can you assign carbons, if you can assign, carbons without a C13 spectrum, is a C13 spectrum necessary? The answer for that is it is necessary for unbiased verification, but not within our structure elucidator tool, as Dimitris answered previously. And then another question was, can you select more than one structure fragment that you're sure about? For unbiased verification, we are limited to one fragment, but as Dimitris mentioned, in the structure elucidator tool, you can define as many fragments as you are confident in. The next question is, taking the best structure from unbiased verification back into auto assignment, is the match factor then higher?
Well, yes, it should be higher, and most probably it will be higher. There is no real reason that it will be lower, and this is why we are doing all this exercise. The thing is that we need to understand how the match factor is calculated. As I said briefly during the presentation, it's calculated based on the deviation of the worst matched signals in the spectra. So if you have 20, let's say, carbon atoms, and 19 of them are spot on, but one of them is, let's say, 20 ppm off, then you will get a low score. If this carbon in the automatically generated structure comes, let's say, to 3 ppm closer, then yes, the score will be higher. So yes, definitely, if you take the generated structure and put it into the standard NMR workbook suite verification, you will get a higher score.
Perfect. I think this next question is, it's related to when you made the jump from CCV to UBV. So maybe just to explain the workflow again so that it's clear, because the question was, does the UBV test the same auto-generated isomers as concurrent verification, or does it generate others? How does it decide what to test? So if you could just briefly mention again about which structure is being used.
So UBV is not checking any structures. Okay, UBV is only taking the molecular formula from a structure. Okay, so it will only take the molecular formula and feed it into the computer-assisted structure elucidation engine. All the automatically generated structures are isomers, so they will have the same molecular formula. So in this respect, it doesn't make any difference which structure you use to start with, as long as they all have the same molecular formula. However, you may want to select, a structure that's somehow closer to what you think it will be, in case you want to predefine a fragment. If you want to predefine a fragment, you should start with a somehow reasonable structure. So that's why you want to probably have the correct structure or your proposed structure selected. But otherwise, it doesn't make any difference, because UBV is not using any of the structures. It's using the molecular formula.
Great. The next question is, what does it mean, or what would happen if the problem from UBV is not rated as easy?
What will happen is that it will probably take longer time. In this example that I showed you, it solved it within a few seconds. If I hadn't defined the fragment, it would have taken, on my computer, around 7 minutes. Now, if it's not easy and it's maybe medium, then it will take probably a little bit longer. So how much the little bit longer is will depend on the actual problem itself and how many possible structures can be generated, how many correlations you have, how many ambiguous correlations you have, if any. And we have seen that usually if something is ranked as easy, it may take maybe up to 45 minutes, 1 hour. If it's ranked medium, probably takes something between half an hour and a couple of hours. There is quite a bit of overlap, of course, in these time durations, and we have seen a few exceptions to this rule. We are definitely looking into refining the ranking criteria for the difficulty of the problem, and as with all of our other tools, we will keep evolving and improving unbiased verification.
Okay. Next question is, what if you misassign your carbon spectrum based on this structure? Does that introduce bias into your unbiased verification? I believe you answered that previously in the sense that it's just using the molecular formula. It's not taking the actual structure into account. So we've answered that question.
Exactly. Yes,
that's
correct. Yes?
Yes. The next question is, what about the discrimination of HMBC cross peaks regarding the J range from 2J to 5J in the UBV tool? Is it taking it for all peaks as 3J?
The default for the HMBC peaks is that they will be 2 or 3J. However, there is also an option which it is automatically activated that lower intensity peaks will be possible to be higher J's as well. So if you have a low intensity peak, it could be 2J or 3J or 4J or maybe 5J if you have something like that. In any case, if some of the peaks in the HMBC are initially marked as 2J or 3J and there are no structure generated, then the advanced tool that exists in our elucidation engine, what we call fuzzy generation, will automatically start extending these correlations and then defining them as maybe up to 4J up until some structures are generated. However, in any case, if you are into this type of problems, then most probably your problem would have been ranked as medium or difficult. So, yeah, it's the best answer to this is, try to record maybe an HMBC spectrum with a different Complete constant or something else that will have clear information content, or maybe try to record some of the more specific experiments like an H2BC, or if you are lucky and you have a very high sensitivity instrument, an adequate experiment.
Great, and we've got one more question here, unless more trickle in during your next answer. How does this, can you comment again on how the software scores the structure? So the difference maybe between match factor and the deviation. And so the second half of the question is based on a database that needs to be created prior to the analysis. The answer to that is no. This is not using the databasing tool, but Dimitris, can you just briefly summarize the match factor for the initial verification and what's used in CCV, and then the deviation score that's used in unbiased verification and our structure elucidator tool?
Okay, so both the scoring methods use our internal predictor databases, and it's based on these ones that we are predicting the experimental spectrum. We are predicting the spectrum for the given structure and compare it to the experimental. We have a very extensive prediction database, so probably one of the best around. You can definitely use your own training databases for the prediction of the chemical shifts, and most probably if you are working with structures that are not known, you will want to use your custom training database. Now, the ranking is done in two slightly different ways. The standard structure verification and combined and concurrent verification are calculating a match factor, which is calculating how well do the worst matching peaks match. The unbiased verification is not using only this, how it is getting the average deviation for all the predicted chemical shifts versus the experimental ones. So the way the unbiased verification is doing the ranking is more, let's say, universal and specific for the way that UBV works, because it's generating structures out of scratch. Now, which one is better? I don't believe there is a clear answer there. They are both very good. So if you have a high match factor and a low deviation, then you are probably very good. Whether there are exceptions that you have a high match factor and high deviation, this could potentially happen if you have very few atoms in your structure and one of them is way, way off. But usually you will have other problems there, and normally you would have rejected that structure before even going to unbiased verification.
Excellent. We had another question come in while you were answering there, is what is the purpose, or why do we need a fully assigned carbon spectrum if it's not using any of the assignments for UBV?
Yes. We need to have the fully assigned carbon spectrum in order to ensure that we are getting the correct peaks from the HSQC and the HMBC spectrum. And we want to have it fully assigned because that would be a very good first step to ensure that we are not hunting for ghosts. Okay, if we don't have a fully assigned carbon spectrum and we have peaks missing, or we have many more extra peaks, then there is probably no point in continuing with UBV. One thing to point out here is that UBV is not a tool that will answer, that will solve your structure. UBV is an extra tool that's used in the whole structure verification workflow. You should not consider UBV to be, let's say, a small version of Structure Elucidator. It is a tool that will help you to ensure that the structure that you are proposing is the correct one. So in this respect, you will use it as the last resort, let's say, as the last tool available, and you don't necessarily, you won't go there if you have so many more pieces of evidence before that to show that the structure is not correct. Okay.
Great. Thank you very much, Dimitris, and thank you everybody for taking the time to join us today. We understand everybody's got very busy schedules, and we hope the webinar was of interest for everybody in attendance. Just to remind everybody that you will receive an email with a link to the recording of this webinar. And if you do have additional questions that do come up, please feel free to contact us and we will gladly reach out to answer any of the questions that you may have on unbiased verification or any of our NMR or other analytical chemistry product offerings. So thank you once again. I hope everybody has a fantastic day and evening, and happy verification, everybody.